3, 2, 1. Alright, okay. Alright, welcome once again to a pre-recorded video. So, we are gonna go over our wonderful problem set here. I'm not gonna give complete solutions to everything, as usual, but I'll give you some tips, tricks, some hints. Alright, so we have 5 very exciting problems, covering a lot of fun material, and let's go through it. Okay, so problem number 1 asks you, if it exists, find the inverse of this matrix right here. And as we noted, a matrix being invertible is equivalent to a whole bunch of things, and the primary, yeah, that word's not sounding right. The main one is that you're invertible precisely if you're non-singular. Our definition of non-singular is that your null space is trivial. So the associated homogeneous system with these coefficients, if that only has the trivial solution, which we have investigated before, and we discovered that for a square matrix, that only happens if you're row equivalent to the identity matrix. So, what does that mean for us? Well, if you want to detect if something is invertible and find the inverse, we will go ahead and set up the following augmented matrix. So, in particular, what are we doing? We will take this matrix and augment it on the right with the identity matrix, right? And the idea there is that, excuse me, just getting it set up. The idea there is that if you augment it with the identity matrix and then perform the row operations, if on the left you get the identity matrix, that means that the matrix on the left is row equivalent to the identity matrix, right? Because the row operations that transform it are being performed on the identity matrix on the right. And here's the augmented matrix. So the idea here is that now we will compute the ref, and the row operations applied here. If this is row equivalent to the identity, we'll pick up the identity matrix on the left, so that will detect if we are invertible or not. And then on the right, what we're guaranteed to arrive at is the formula for the inverse of A. And the way we justified that was noting that kind of what you're doing is you're simultaneously solving 3 different matrix equations. AX equals the standard basis element E1, AX equals the standard basis element E2, that's this one right here, and AX is equal to the standard basis element E3. And as we learned, the solution to those are going to give you the columns of A inverse. Alright, so you simply set that up and find its ref, and I'll leave you to do that. Obviously, I'm not going to do the entire problem for you. Alright, that's the idea of how to find the inverse of a matrix. We augment it with the identity. On the left, when we perform the row operations, if we get the identity, we know we are invertible. And on the right, we are simultaneously solving the equations. AX is equal to the standard basis elements, the solutions of which will give us the columns of the inverse. Cool. Alright, so there you go for number 1. Alright, now coming up here, we have 3 proofs in a row. 5 is sort of a proof, but not really. We'll talk more about 5 when we get there, but 3 proofs coming up here. Alright, so this one is an all-time classic. We're asked to take a square matrix, A, with the further assumption that squaring it gets us the zero matrix. And as we discussed, these are matrices that are called nilpotent. And in fact, it does not need to be a square here. A similar problem can be done for any power. It gets a little bit more interesting. But a really neat property of nilpotent matrices is that the identity matrix minus A is invertible, and the inverse has a pretty neat formula. Alright, so if I want to demonstrate that a matrix is invertible, one thing you can do, of course, is augment it with the identity matrix and perform row operations. But another way of doing it is to give an explicit equation or formula for the inverse. And here we were kindly given it. So, excuse me. Right, let's go ahead and pull the following move. I am claiming that the identity matrix minus A times is invertible, and that its inverse is I plus A. So if that's true, then this product here should give me the identity matrix. Right, and then if that's true, then I know that this thing here has to be the inverse. And as we proved, it doesn't matter if you show this is the identity matrix or if you show the reverse product with plus or minus. So your starting step could be the one I have right here, or your starting step can be this one right here. In either case, if we get the identity matrix, we know that then the other product also has to equal the identity matrix, something we proved, that if a product of two matrices is equal to the identity, then, so if A times B is I, then B times A for square matrices is also necessarily equal to I. So it doesn't matter which one you prove. Since I've already got this one on the screen, let's do it. And let's recall that our good friend FOIL is still true. So again, that means that when you're producting a pair of summations, as we have here, you do the first multiplied together. So in this case, that will be I times I. So first, then outer, and in our case, that would be I times negative A. All right, so the outer terms. So we had our first I times I, then the outer terms I times negative A. Then the inner terms A and I. So we'll have an A and an I. And then last, the last terms. So the plus A and the minus A. Right, so our favorite maneuver that we learned back in the day is still true for matrix multiplication. All right, and now we could start cleaning some things up here. The identity matrix times anything gets you whatever you're multiplying it by, which in our case is the identity matrix. And so the identity matrix times negative A will give me a negative A. The identity matrix times A will give me a positive A. And then A times negative A, well, we can factor out that minus sign, as we proved. And then you have A times A, which gives us A squared. All right, and lo and behold, a bunch of magic now happens because we will have minus A plus A, which is equal to 0. And then we have negative A squared, but A squared by hypothesis is indeed equal to 0. And there we go. Proof is over. All right, not too bad. Okay, pretty cool. All right, so that takes care of problem number 2. Let's keep keeping on and head on over to problem number 3. And problem number 3 is a really fun one. I love this one. Took this one out of your textbook. I never considered this one before until your textbook said, hey, prove this. And I was like, ooh, this is a fun one. All right, so if you take an m by n matrix and a invertible n by n matrix, it turns out that the column space of A coincides with the column space of A times B. All right. So I'm being asked to prove that two sets are equal. So how do we do that? Well, let's start off with I'm going to pick the simple B to be in the column space name of A. So we're asked to prove two sets are equal, and generally speaking, there are two main methods of doing that. You either directly show the sets are equal through some set operations or some other known facts, but more commonly, what I'm going to prove is that any element of this set is an element of this set, and vice versa. Alright, so let B be an element of the column space. Now, the column space, recall, one of our fundamental subspaces, has a couple of interpretations. It's the span of the columns. It is also the collection of right-hand sides so that the matrix equation AXB is a solution. Or more particularly, there has to exist an X out of, and we have an M by N matrix in this case, so there has to exist an X out of Rn, such that B is equal to A times X. Right. So again, another way of thinking of it is it's sort of the right-hand sides that ensure the matrix equation, the associated system of linear equations, is in fact consistent. Right, it's a little clunky to say, but generally, right, it's the things that are equal to A times X. All right. Okay, so what do I need now? Well, now I need to prove that not only is b equal to an a times x, but b is also equal to an a b times x. So I need to think about, okay, well, how do I do that? All right. So, give me a second. So let me go ahead and write that. So what I want is b is equal to a times capital B times. And I'm going to write y because I don't necessarily know what it's going to be. Right, so I want this to hold. Okay, and that gives us a bit of an idea. Because, and we'll kind of, let me put this down here on this line. We'll do this as a little sort of proof scratch work. Right, what I want to prove is that that is true. Right, because that'll give me that b is in the column space of a times b. So if I look at what I know that b is equal to a times x, and I want b is equal to a times b times y. Well, that would mean that b, capital B, times lowercase y has to equal x. And what do we know about our matrix B? We know it's invertible, and that means I can multiply by its inverse over to the other side. Oh, where's the equality sign? Where'd that go? Right, remember, if you are invertible, I can multiply both sides of the equation by B inverse, and, well, then we get the identity matrix on the left and the B inverse on the right. So inverses, right, work just like they did before, multiplicatively. And this reveals that, hey, that gives me my y that I'm looking for. All right. So, now note, this is kind of scratch work right here. This is not a proof, so let's now actually write a proof here. All right, so what do I want to look at? Well, let's look at the matrix A times the matrix B times the vector B inverse times X, right? So now I'll sort of clean that up because now I know what I want to look at is this, A times B times Y, but the Y I figured out had to equal B inverse X, all right? Well, as we proved, and as I made a very big deal about proving, matrix multiplication is an associative operation, meaning that I am allowed to move my parentheses around, and specifically I can move these over like that. All right, and there we'll pick up the identity matrix, and from there we will then pick up A times X, but we know that's equal to B, and there we go. We have now proven that, and let me put some more parentheses at the start here. We now have at the matrix A times B, there is a vector that when you multiply that matrix by it, you get B, and that's precisely what it means to be in the column space. So because B is equal to the matrix A times B times a vector, it's got to be that we're in the column space, and hey, there we go. First part of the proof completed. If I take an element in the column space, it has to be in the column space of A times B. And note here we use the invertibility of our matrix B. All right, but the proof's not over now, because now you have to do the reverse inclusion. So now you will go ahead and let B be an element of the column space of A times B and prove that B has to belong to A, and I will leave that for you to finish. All right, cool. All right, got a couple more problems, and I'll finish up our little proof powwow for the day. All right. So let's go ahead and tackle this one. So if we have a vector space V and a non-zero vector X, and we've got scalars alpha and beta with the property that alpha X is equal to beta X, then the scalars need to be the same. So here we see that you kind of have like a cancellation in vector spaces. So for non-zero vectors, they can be removed to demonstrate that our scalars are the same. Indeed, I'll give you the first line, and then I'll leave the rest to you. As I mentioned in class, we proved a result that will immediately get us this, but we have to make the right first move. And the right first move is as follows. And I'll write... Alright, now since alpha x is equal to beta y, well, when we take their difference, you'll get the additive identity. Right, that's just how it works. And from there, we know that the x can factor, and you'll have alpha minus beta scaling x. And now, at this point, you can go ahead and apply a result from class, and you'll immediately get the solution. And I'll leave that for you to figure out. All right, next up. All right, and I see a bit of a typo here. All right. Fix that, but all right. So let's go ahead and do the following. I have a vector that lives in R3. I've labeled the coordinates R, S, and T. And I know that my R, S, and T satisfy these two equations. I want you to prove this is a subspace of R3. Now, note I said verify. So you can rigorously prove this by going through the axioms for a subspace. You can verify that the set is containing the additive identity, and then show that it's closed under scaling and adding. That will give you that it's a subspace. But there is a faster method here, because I'm going to go ahead and create a matrix. And specifically, I'm going to create a 2x3 matrix. And why would I do that? Well, I have two equations and three unknowns. So what I'm going to pull here is reformulate the set W in terms of a matrix. And in particular, we will get this matrix as the fundamental subspace of a matrix A. All right. And it's a little easy to pull this off, but you gotta kind of have an eye for it. So I am currently concocting the matrix. And I immediately messed it up, but don't worry, I fixed it because I looked at it and I was like, wait a minute, that's not right. All right, and we got it here. Okay, so my plan of attack here is to actually demonstrate that my set W is, in fact, the null space of a particular matrix, this one right here. All right, so note, two equations, three unknowns, so A, it's a 2x3. I have two equations and three unknowns. All right, and then note that this matrix A times our vector RST. Oh, there it is. All right, so note that if we take our matrix and multiply it by this vector RST and set that equal to 0, well, on the left, we can rewrite that as follows, because we know what our matrix is. It's that right there. And the 0 vector in this case will be a element of R2. Right, because we'll have a 2x3 multiplying a 3x1, giving us a 2x1. All right, then that holds if and only if what holds. All right, well, do out the matrix multiplication. So we'll have 5r minus s minus 2t is equal to 0. And do out the matrix multiplication again. So I have a negative 3r minus 7s plus 16t. Equaling 0. Alright, so I'm just doing out this matrix multiplication. It's equal to 0. Alright, which is equivalent to what? Well, if we rearrange the ingredients in my equation, the top equation will become, the first equation will become 5r is equal to s plus 2t, and my third equation will become, I lost my t on my 16, will become 16t minus 3r is equal to 7s. All right, and therefore, what have we just done? Well, we've demonstrated that my set W is, in fact, equal to the null space of our matrix A. Hey, there we go. And we pulled off a similar thing in class. And note that now, of course, you'd want to note that this guarantees that W is, in fact, a subspace, but again, I'll leave that to you. And there we go. Wonderful little review of our problem list. So I'll leave it to you to finish it and hand it in class this upcoming Friday. All right, and I'll see you in another pre-recorded video on Thursday where we'll talk about spans a little bit more. We'll talk about subspaces a little bit more and define spans in the context of vector spaces. All right, so I'll see you next time.